Hi, my name is Maddie Gaines, and this is my Lab 5 Magnetic Braking with Faraday for Physics 2 at Georgia Tech. The purpose of this lab was to investigate the interaction between a falling bar magnet and a conductive tube made of aluminum foil. The goals included collecting observational data of a magnet falling through the conductive tube, model the magnet-tube interaction computationally, and compare the computational predictions with the observed data. We figured out that our results showed our experimental time was 2.04 seconds and our computational model time was 1.91 seconds. The magnet ended up falling slower because of resistance, and eddy currents were visible throughout the tube. Slower descent and potential change, which was different than compared to free fall. Faraday's law is a changing magnetic field induces an electric field, which in turn can generate an electromotive force and drive current in a closed circuit. Lenz's law states that the direction of an induced current in a closed circuit opposes a change in magnetic flux that caused it. For magnetic fields and forces, the interaction between the falling bar magnet and the induced currents in the conductive tube creates magnetic fields that exert forces on both the magnet and the tube. The Biot-Savart law relates the magnetic field produced by a current-carrying wire to the current and the distance from the wire. Newton's laws of motion are used for analyzing the motion of falling objects and the forces acting upon them. Newton's third law specifically states that the force exerted on an object has to do with the current carrying rings. In our experiment, the system was the bar magnet and the surroundings was the aluminum foil and everything else. For our assumptions, we said that air resistance was negligible and the location of the magnet doesn't change. For the experimental parameters, the length of our tube was 0.305 meters, the width was 0.005 meters, and the magnitude of the magnetic dipole moment was 2.38 am squared, and the average time was 2.04 seconds. For the overview of this experiment, we found the north end of the magnet, dropped the magnet through the tube, and repeated these steps 5 times to get an average. So these are the first couple of steps of my GlowScript code you can see that I'm creating the tube of aluminum foil, the properties of the magnet, initial conditions, and created a function to calculate the magnetic field. And then finally in step 3, you can see that I created a function to calculate magnetic flux. In this next lines of code, I edited to compute a typical B field of each ring, and I found the gravitational force. I found the net force on the magnet, and I updated the magnetic's velocity and position throughout these lines of code. In the velocity versus time graph, we see that there's a high initial velocity downwards, and that velocity decreased and was constant within the tube. Velocity increased when the magnet left the tube. The simulation average time in the tube was 1.91 seconds, and the actual average time in the tube was 2.04 seconds. Some evaluations of error could be human error or electromagnetic interference, and there could also be neglected factors like air resistance or external forces, which we stated in our assumptions in the introduction slide. The red current is clockwise, and the blue current is counterclockwise in the tube. The induced currents reverse their directions, and the magnetic fields look opposite now. The total time was larger in the actual model than the simulated model, and computational could be made more accurate if we consider things like air resistance or outside electromagnetic interactions. The velocity versus time graph, gravity was acting on the magnet, that's why we saw a decrease in the velocity, and the net force is 0, which we know because there was a constant velocity. The dynamics of the falling magnet would change because there would be a larger induced current and a larger magnetic force from this current. This would cause just an increased force on the magnet in general, and the magnet would take longer to get through the tube. If holes or slots were cut into the tube, the induced current would decrease, and so would the magnetic force. The magnet would take less time to get into the tube. Thank you for watching my Physics 2 Lab 5 of Faraday's Law.